we'll get going then with chapter 6. So chapter 6 is going to be all about chemical composition. So again, I've mentioned this a couple times, but we have these sort of like stacks of concepts that we're building. We're still working, I guess, sort of on the second stack where we've talked about atoms, what atoms are made of, talked about how atoms can combine into molecules or compounds, and then also how those compounds can combine into different things. We've covered atomic mass is the average of all the masses of the isotopes. Oh shoot, there's another one. Oh, we've talked about sort of chemical changes as well, where we're changing the exact proportions. Oh, this was the one I was thinking of. Conservation of mass, right? Or conservation of those atoms. Whenever we go through a chemical process, the atoms that you start with are going to, there's going to be the same number of atoms that you started with, that you end with in any chemical process, but they're going to be rearranged. So that's kind of, we're building on that here now. So sodium is an important dietary mineral. It's one that's very, very easy to get. And it's in table salt, right? It's sodium chloride. So sodium is involved in the regulation of body fluids, and eating too much of it can lead to high blood pressure, which is due to osmotic pressure, which might be at the end of this chapter. Oh, no, that's chapter 15. Essentially, if you have too much salt in your blood, it draws water out of your cells, which increases your blood pressure. It just, it fell off the stand. Are you kidding me? Like it's literally like you can thumb screw this. And somebody didn't do that. God. Really, college almost bought me a new iPad and a new laptop. Okay. Destructive technologies aside. Oh, scratch the screen. Well, that's their fault. The chemical composition of sodium chloride, which we've looked at it several times now, is sodium and chlorine. We've talked about how to name these things, right? So there's one sodium ion to every chloride ion, because it's the ion of chlorine. So it's an ionic compound. Since the masses of sodium and chlorine are different, the relationship between the mass of sodium and the mass of sodium chloride is not clear from the formula alone. Oh, that reminds me, I did skip the end of chapter 5, didn't I? There's one last thing in chapter 5. Very briefly go back to this, because, okay, very quickly, there's this concept of formula mass, which I think should be at the beginning of chapter 6. And this actually does tie in with this very well. So if we were to, maybe I'll do this again. If you were to look at the masses of sodium and chlorine on a periodic table, you can look at these masses and you can see that, is this a good one? It's not a good one. Give me one with the masses, please. Well, I guess there's not going to be anything that's big enough for you to see unless I opened it on here. Okay, so if you look at the masses of sodium and chlorine, sodium has a mass of now these are all horrible. Why is it so hard to Google a periodic table and get a good one? The masses are different. So whenever you want to calculate the mass of a compound, you need to know what the atomic masses of the different components that make it up are. This is the website that I usually use. So the mass of sodium is 22.99. The mass of chlorine is 35.45. So just based on the mass of sodium, or just based on the formula, sodium chloride, you can't say anything about what the mass proportion is of either of those. We have 22.99 for sodium, 35.45 for chlorine. And these are units of grams per mole, grams per mole. So the formula mass then is the sum of all of the atoms of the first element in the chemical formula times its atomic mass. So in this case, we have a number of atoms in the first chemical element in the chemical formula. We have 1 sodium. We're going to multiply that by 22.99. Sorry, I'm not switching tabs. And then we add that to the number of atoms of the second element, so in this case, 1 chlorine, times its atomic mass from the periodic table, which is 35.45. And then if we had more atoms or more different types of elements in our formula, we would keep going. So the number of each atom times the mass of that atom to get the total formula mass. So in this case, we're really just going to have 22.99 plus 35.45. Oh, I multiplied them. Add them together. Plus, parentheses. And you get a total mass of 58.44 grams per mole. And that's the formula mass of sodium chloride. All right, so it's the masses of all the things that make it up. So something analogous would be if you had a bicycle and you say you have 1 frame, including the seat and all the other things. We'll simplify it. You have 1 frame, you have 2 bicycle wheels. So you have to add up the weight of each of the bicycle wheels plus the weight of the frame will give you the total weight of the bicycle. And I guess to extend that analogy a little further, in different chemical compounds, you're going to have, maybe you're doing mountain biking, so you've got heavier wheels. Or you're doing road biking, so you've got lighter wheels. You're going to have different masses of each of the components, and it's dependent on the type. So we want to do this for nitrogen monoxide, dinitrogen monoxide. All right, so we've got nitrogen, oxygen. This is usually the way that I do it. You can just write them out in a list. And then we'll say that, all right, we have 2 nitrogen atoms, because there's a subscript 2. And we have 1 oxygen atom. I know this periodic table is too small to read. Can't believe that this room does not have a periodic table. But I think I can do this pretty quick. Sorry, I gotta do something for Zoom. Glimpse into the matrix. Okay, so we got a periodic table here, still not super easy to read. So we have nitrogen, nitrogen's over here. The periodic table, oh yeah, this is a good note. You won't need this for this upcoming exam. For future exams though, the periodic table has masses on it with different precision than this. Right, so that's 14.007. I believe the periodic table that I use uses 14.01. So not as precise, but make sure you use the ones that I have on the periodic table. So 2 times, we'll use this for now though, 14.007. Right, so that's the mass of a single nitrogen. Oh, you can't see that. All right, so 14.007. And then we can go find the mass of oxygen. And we'll add that in here as well. So it'll be 1 oxygen atom times 15.999. You can set hotkeys for these. But I haven't done that. All right, so the mass of nitrogen, 14.007, times the number of nitrogen atoms. Just like for a bicycle, you would have 2 wheels. Our dinitrogen monoxide has 2 nitrogens. So then we do this multiplication. We get 14.007 times 2 will be 28.014 and 15.999. And because we want the mass of the whole thing, we'll add these together for a total mass of 44.013 grams per mole. And here we would, again, use the same number, or the same precision that we have as a part of this calculation. So each of these has 5 sig figs. This is one of those situations where we have exactly 2 nitrogen atoms. So that's an exact number, has an unlimited number of significant figures. And then when we do this addition, all right, we keep the smallest number of decimal places, and both of them have 3. So you have 44.013 grams per mole. This equals the formula mass. Give me this, yeah. Of dinitrogen monoxide. Okay, so that's the concept that we're working with here with sodium. In that sodium and chlorine have different masses. So the relationship between the masses of sodium and the masses of chlorine is not 1-to-1. Right? We can't say that if we had 10 grams of sodium chloride, we would not have, right, equals the slashes does not equal 5 grams of sodium plus 5 grams of chlorine. We don't know how much it is. We'll get to how you can calculate it later. So we need to calculate the amount of a constituent element in a given amount of a compound. And that'll be dependent on its mass, or its formula mass. Is everybody done with the slide? I am trying to slow things down a little bit. I know I go fast. All right. So the amount of element in a compound can be calculated using the chemical formula along with the masses. Right? So we had the formula mass, or we can use the atomic masses to get the formula mass. So let's say this mining company needs to know how much iron is in a given amount of iron ore. Right? So for every rock that they pull out of the mountain, how much of that rock is actually iron and how much of it is other stuff, because there's always other stuff. Or if you're estimating the threat of ozone depletion, requires knowing the amount of chlorine in a given amount of chlorofluorocarbon, which is a refrigerant that's not used anymore. You might hear old people complaining about car AC not being as cold as it used to be. It's because we don't use Freon anymore. It destroys the ozone. So if you want to know how much of these, how much of the, maybe dangerous component of a chemical is present or is in a certain amount of mass, or if you want to know the amount of iron, you need to be able to count those individual atoms, really. And because we can't actually count individual atoms, we can do it sort of by proxy, kind of do it in a roundabout way. An analogy for this would be selling nails by the pound. So if you need, hundreds of nails to build a house, you're not going to go to the store and say, I want, 10,000 nails. They're not going to sit there and count them out one by one for you. They're going to say, oh, well, here's 5 pounds. It's probably more than 5 pounds. Here's 5 pounds of nails, though. That should be about 10,000. So instead of counting them, we can say one nail weighs however much. So 10 pounds of nails, 5 pounds of nails should have this many nails in it. So this is similar to our problem with how many atoms are in a given mass of an element. So if you took a bottle of water and said, how many atoms of water are in here? Well, we're not going to count all the atoms, can't do that. But we know how much a single atom weighs. So we can say that if a single atom weighs this much, and we have this much mass, then we can do the math and say that there must be this many atoms of water to create this mass. The analogy then continues that different size nails are going to weigh different amounts, right? A bigger nail is going to weigh more. So in a pound, you'll get fewer nails. So say that we have a customer. They buy 2.6 pounds, 2.60 pounds of medium nails. And a dozen nails weighs 0.150 pounds. So we can say 12 nails. Well, even better, we could say 12 medium nails weighs 0.150 pounds. So how many nails did this person buy? At this point, you should look at this and think that that looks like a conversion factor, and it is. All right, so we can do this two ways. One, we could figure out how much one nail weighs. And to do that, we could say, well, if 12 nails weighs 0.15 pounds, how much does 1 pound or one nail weigh? Yeah, divide the weight. I think that's what you said. So we take 150 or 0.150 pounds divided by 12 nails. Whoops, nails. And we'll get, let's see, what would that be? 0.150 divided by 12. Myself a little more room here. 0.0125 pounds per one nail. I'll say we can also do this the other way. We're going to figure out how many, if this is how many nails there are in 0.15 pounds, how many nails would there be in 1 pound? So you just flip this. So 12 nails in divided by 0.150 pounds. So 12 divided by 0.150 will actually give us, 80 nails. Not worrying about significant figures here yet because, well, we're not reporting an answer yet. So you can do this other way. Oh, sorry, this is nails per 1 pound, which looks more like a 1. So in your conversion factors like this, when you divide by one of those things, you're actually figuring out how many nails per 1 pound or how many pounds, nails per 1 pound or how many pounds per one nail. So we can use either of these conversion factors because actually if we flip this upside down and we do 1 divided by 80, we will get this number. So they're interchangeable.
So was it like the same answer? Did we get the same answer, or how did that work?
Yeah, so if you want to take your calculator, or here, I can do it on here too. Pull up this one. I don't like this calculator, which is why I don't use it very often. So 1, and I hit divided by 80 equals 0.0125. Oh, man.
So why would you flip that?
Did I do that? No, we don't like that. It's because the aspect ratio of the screen is weird. So it's 0.0125. Sorry, what did you say? Why would you?
Yeah, so why would you flip it? Why would you flip the 80?
To make it a little easier to work with, because you can use either one.
Oh, okay.
You can use either one, yeah. So, I mean, we can do this both ways. And this works for all conversion factors, by the way. If we have 2.60 pounds of medium nails, we want to convert that into how many nails we have. So we do 2.60, and then let's use the 0.125. 0.0125 pounds per one nail. Oh, sorry, I did that upside down. We have to flip this. Right, because if I put nails on the bottom, nails is the unit we want. One nail, because here we've units of pounds, so this is 0.0125. Right, that's the mass of one, or the weight of one nail. So now I do 2.60 divided by 0.0125 is 208 nails. But we could also do this as, let me make this just a little bit smaller. We could say we've got our 2.60 pounds. I'm not going to write out the whole thing. And we know that that's also 80 nails in 1 pound. So I used to do 2.6 times 80. And also gives us 208 nails. Oh.
Are those all different ones, or all the all same?
Sorry, what was that?
Are those like all different questions, like either different questions at the bottom?
No, so each of these is answering the same question. How many nails are there in 2.6 pounds? So as long as you have your conversion factors set up correctly, by which I mean that, right, a single nail, if 12 nails weighs this much, then one nail should weigh less than that, sort of thing. Yes, yeah, so you could set this up also as 2.60 pounds times 12 nails over 0.150 pounds. And you'll also get 208 nails. So as long as you have the correct conversion factor, and you set up the units correctly, because on each of these, notice that we have pounds, pounds. This is pounds, 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 pounds. You'll get the right answer. Which distracts a little bit from the point here, being that we can use the weight, the mass of a dozen nails, to calculate how many nails you buy in 2.6 pounds, and 10 pounds, and 100 pounds, it doesn't matter, based on the mass of 12 nails, or 1 nail, or 80 nails. So atoms are similar in that we don't want to sit around and count individual nails, don't want to count atoms. And then we have all the masses of the atoms, if this is still on the periodic table. So if you think of like medium nails versus small nails, we've got our smallest nail is hydrogen, and our largest nail down here about with oganesson. So we can use their mass and the mass per a number of nails to count them. Yeah, even if you could see atoms and counted them for 24 hours a day, as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand, because there are just so many. Oops. So a dozen is a convenient number for nails. It's also a good number for eggs, or for most things, really. But because atoms are so small, we need a much, much bigger number to count them by. So the number that we use is called the mole, abbreviated MOL. So 1 mole is this really, really big number. 6.022 times 10 to the 23. And it's also called Avogadro's number, named after Amadeo Avogadro, who did the math. Yeah. So this is the number that we're going to use throughout the rest of the semester, and if you do more chemistry, throughout the rest of chemistry, to count the number of atoms. Usually we count them in moles. So 1 mole of atoms, ions, or molecules generally makes up objects of reasonable size. So if you have a mole of copper atoms, then that's about 22 pennies. So in here, there are 6.022 times 10 to the 23 copper atoms. 1 mole of helium atoms is about 2 balloons. So in each of these balloons, or in these balloons combined, I should say, there's 6.022 times 10 to the 23. I'm just going to abbreviate helium atoms. So that's why we use the mole. Because even though there's literally an unimaginable number of the atoms or molecules, this is a workable scale. So if we wanted to do the math, the numerical value of the mole is actually defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. So it's a carbon with 6 protons, 6 neutrons. And if you took this 12 grams and you divided it in half 79 times, you would get a single carbon atom. So based on this, if you have carbon-12 in 12 grams, 12 grams of carbon-12 equals 6.022 times 10 to the 23 atoms. I'll even go so far as to say atoms of carbon-12. Which one?
Where you got that carbon-12?
Oh, the carbon-12?
Yeah.
Well, that was just this right here. Yeah, so exactly 12 grams of carbon-12 is 1 mole.
And then how'd you get the 6?
Because this is, sorry, this definition of the mole establishes, I'm on the eraser.
Oh, it's a 1 mole, right?
So it was, Avogadro did the math to say that there are this many atoms in 12 grams of carbon-12. So then we can count the number of atoms by weighing them, rather than one at a time. So we can convert between the moles and the number of atoms like we converted other things, right? This is a conversion factor. 12 grams is this many atoms. Or a dozen nails is 12 nails. So 1 mole, this really should say 1 mole of atoms, is 6.022 times 10 to the 23 atoms. But you could have 1 mole of anything. It's just like a dozen. You could use it to count things. You could have a mole of eggs. You could have a mole of marbles. You could have a mole of chocolate bars if you're hungry. You have to be really hungry for that much chocolate. I don't think that amount of chocolate has existed. So we can convert 9.5 times 10 to the 27 atoms to moles. And anytime that we're converting from atoms to moles or moles to atoms, it's always going to be 1 mole is 6.022 times 10 to the 23 atoms. Doesn't matter what type of atoms. So we'll start with our 9.5 times 10 to the 27 atoms. And we want to cancel this out. All right, cancel out the units. So we'll have 6.022 times 10 to the 23 atoms is 1 mole. So 9.5 times 10 to the 27 divided by 6.022 times 10 to the 23. That's going to be, I'm just going to put this right into scientific notation, 1.6 times 10 to the 4 moles. Or if you like, 15775. So this one would have the correct number of sig figs. There it is.
May I have your attention, please? This is Atlas IED.
Okay. Is everybody good on that? So say we have a gold ring that contains 0.83 times 10 to the negative 2 moles of gold. So we just start with, 8.83 times 10 to the negative 2 moles of gold. And now we want to convert from moles into atoms. Starting with mole here, we're going to go to atoms. So this is going to be 1 mole is 6.022 times 10 to the 23 atoms. So we'll do 8.83 times 10 to the negative 2 times 6.022 e to the 23. We end up with 5.3174 times 10 to the 22. But we only have 3 sig figs, so 5.32 times 10 to the 22 atoms gold. So it's just another special conversion factor. It's not even that special. It's just a really big number. Okay. So we can do moles to atoms, but it's not super useful.
May I have your attention, please? This is Atlas IED.
It's not super useful because we can't ever count atoms anyway, really. So it's a lot more useful to go from moles to grams. So we talked about how you can count the number of nails in a certain weight of box, right? So you have 10 pounds of nails. You can do that for atoms as well. But each atom has a different mass. Is this still on? Yeah, so like hydrogen has a mass of 1.008. But something like silicon has a mass of 28.085. So silicon's 28 times heavier. And these are the masses of our nails, or the atomic masses on the periodic table. So that's our molar mass. It's the mass of 1 mole of atoms of the element, which is numerically equal to the atomic mass in grams. It's mass of 1 mole, mass of 1 mole. Sorry, this is what I was looking for. Mass, 1 mole. So for hydrogen, these units of mass on the periodic table are in grams per 1 mole. All right, so this would be for hydrogen, and then silicon was the other one, 28.085 grams per 1 mole of silicon. And for carbon, or for carbon 12, it's exactly 12 grams. So now we can use these instead of counting, instead of using the masses of the atoms, we can use the actual number of moles, which is going to be super important because when we do chemical reactions, we're converting them on an atom-to-atom basis. But we can't weigh out atoms, so we use grams. So, right, comparison between, again, let's say hydrogen, which is 1.008, or silicon, which would be like a large nail, maybe a medium nail, to be honest. So 28.0. All right, so different masses means you're going to have different numbers of, or you're going to have different masses for different numbers of nails. So one mole of silicon is 28 grams. 1 mole of hydrogen is 1 gram, where a dozen large nails might be 0.5 pounds, whereas a dozen small nails might be 0.1 pounds. So you need the molar mass in order to calculate. And actually, we have a great lab where you'll do this. So similarly, 1 mole of silicon, or sulfur, weighs 32 grams. So you need 32 grams of sulfur to get 1 mole, whereas 1 mole of carbon only weighs 12 grams. So in not this week's lab, but next week's lab, I think, it's called the mole, you'll go through and you'll weigh out 1 mole of different elements. So like copper and water and different things. You can see how those are different. So this is what I was talking about, where 1 mole of atoms, the mass of 1 mole of atoms changes for different elements. So 32 grams for sulfur, 12 grams for carbon, 6.94 grams for lithium. But each of these masses is equal to 1 mole of those atoms. So for lighter atoms, less mass, and 1 mole. So we'll use this very frequently, this molar mass, to convert between grams and moles. I will sometimes ask you to go from moles to number of atoms or atoms to number of moles, just to help test that concept. But between grams and moles is the real convenient conversion factor, right? Because moles is just like saying 1,000 cars or 1 mole of cars. Just waiting until the scribbling stopped. So we can calculate then how many moles of calcium are in 91.4 grams of calcium. So you have 91.4 grams
May I have your attention, please?
calcium. And calcium is 40.078. Let me do this. So it's 40 point, right? Still a good idea to write out all of the things that you're given and what you're asked to find. All right, so if these are our givens, 40.0, I think I said 78 grams of calcium per 1 mole of calcium. We want to find moles of calcium. So it's just a conversion. So we're still just going to do 1.4 grams of calcium times. Now, do we want grams on top or grams on the bottom for our conversion factor? Yeah, we want grams on the bottom because we have grams here and we want to cancel that out. So we'll do 40.078 grams of calcium is 1 mole calcium. So then it's just 91.4 divided by 40.078. It's going to be 2.2805529. So then with the correct number of sig figs, we'll have 2.28 moles of calcium. So hopefully you remember me saying how understanding how to do conversions was going to be super, super important. It's because these are the conversions that we'll be doing the rest of the semester, going back and forth from grams to moles. And so it's a lot easier to know, cancel these units, rather than trying to remember every single time I'm going from grams to moles, I divide, versus going moles to grams, you multiply. So this is for, right, 91.4 grams of calcium. If we wanted to figure out the number of moles of something else that was 91.4 grams, we'd have to use the atomic mass or molar mass from the periodic table. Speaking of something else, now we're doing the opposite though. So I know the number of grams of sulfur in 2.78 moles of sulfur. So again, we're given 2.78 moles sulfur. And we need the molar mass of sulfur, which is 32.06. Grams of sulfur per 1 mole of sulfur. We want to find grams of sulfur. So we start with 2.78 moles of sulfur times our molar mass here. So because we want moles on the bottom, 1 mole sulfur is 32.06 grams of sulfur.
May I have your attention, please? This is Atlas IED.
And then we just multiply. 89.1268, or with our 3 sig figs, 89.1 grams of sulfur. So it is just another conversion. We just got a whole new set of conversion factors on the periodic table, and a new unit to work with in moles. So how many carbon atoms now are in a 0.58 gram diamond? So we're given 0.58 gram diamond. which this does sort of presuppose you know what diamonds are made of. And we want to find oh, well, I guess it kind of tells you carbon atoms, right? So we want to find the
May I have your attention, please?
how many
Atlas IED.
atoms of carbon. So carbon is one of the ones that I don't have to look up. 12.01 grams of carbon per 1 mole of carbon. And then in a question like this, if it's asking for atoms, or if I ask you to solve for atoms, I want you to go all the way from moles to individual atoms, so using Avogadro's number. So our other conversion factor here is going to be that 1 mole equals 6.022 times 10 to the 23. So starting with our 0.58 grams of carbon, we need to divide by grams. So 12.01 grams of carbon, that's going to be 1 mole carbon. And now we want to divide by moles and multiply by Avogadro's number. So when we do that, get 2.9082 times 10 to the 22, or using the correct number of sig figs, 2.9 times 10 to the 22 atoms of carbon. So whenever you're going from moles to atoms, you should end up with a ridiculously large number, because you multiply by 6.022 times 10 to the 23. And so it's a 1 with 23 zeros. Or it's a 6.022 with 23 zeros. So the key here is that asking for atoms is different than asking for moles, is different than asking for grams. So we can do this going all the way the other way. If we're starting with helium atoms, first of all, it'll usually be accompanied by a very large number. So if we're given 1.23 times 10 to the 24 atoms of helium, we want to know the mass, right? How many grams of helium? We've done this a few times, so I'll ask you now, what conversion factors do we need? Which one do we need first? Atoms and moles? Yeah. 6.022 times 10 to the 23 equals 1 mole. And then the other one that we need, helium, yeah, grams to moles. So that's going to be 4.0, I think it was 4.0026, right this way. So starting with this, 1.23 times 10 to the 24 atoms of helium. Our first step will be converting those atoms into moles. So I always think about this as what we cancel. So we're going to cancel out the atoms. So 6.022 times 10 to the 23 atoms is 1 mole. And then we want to go from moles to grams. 4.0026 grams per 1 mole helium. So we will get 1.23 e to the 24 times 4.0026 divided by 6.022 e to the 23. Actually, even with moving that over, it's not enough space. It's going to be 8.17535 grams of helium. But we only have 3 sig figs from our initial number. So we will end with 8.18 grams of helium. Yeah?
So where are you getting like the numbers of like the helium with one to 1 mole of helium?
This one?
Yeah, like where did you exactly get them?
They're on the periodic table.
Oh, okay.
Yeah, so for helium,
It's gonna be the atomic number. I mean the mass.
yeah, the atomic mass. Yeah, the atomic mass. Yeah. Any other questions? Yeah.
Yeah, so for the number of sig figs, right, so you're just looking at the initial number, right?
Yeah.
Okay.
Yeah, the only time that you don't, so, because we're just converting here, right?
Yeah.
So, especially when you're using as much precision as we're using here, this is more sig figs and this is more sig figs than this. And that's usually the case.
Okay.
When that would not be the case is in lab, and you measure actually today it'll be important, because you're going to measure the volume of something, and you're going to get the mass of something, and you're going to calculate density. So you use the lowest precision on either of those, or between the two of those, for your final reported answer. Yeah. So if 22 pennies is 1 mole of copper atoms, right? 6.022 times 10 to the 23. Then that many pennies would cover the entire Earth's surface to a depth of 300 meters, which is like over 1/4 of a mile deep of pennies, including the oceans. That's way too many. The number's just too big. For one crystal of granulated sugar, it has a mass of less than 1 milligram and a diameter of less than 1.1 millimeters. But 1 mole of sugar crystals could cover the entire state of Texas to a depth of several feet. It's like these are just like, I mean, I've seen several TikToks actually that talk about how like human brain is not capable of processing super large numbers. If you think about how far away do you think the moon is? It's pretty far. Relatively speaking, yes, it is just right there. You can fit all of the other planets, like edge to edge, between the Earth and the moon. There's actually space left over when you do that. So, yeah. But, I mean, you hear, I want to drive my car to the moon, which is like 248,000 miles. It varies a little bit. But like that's how far that is. That's longer than the diameters of all the planets. Just like, I think anything over like 1,000 is just too hard to think about. Anyways, so this is why these numbers are like way too big, so we simplify them. We just call them moles. We can deal with them on an easy scale, usually between like 1 and 100. So for elements, the molar mass is the mass of 1 mole of atoms of that element. We already talked about formula mass today. For compounds, the molar mass is the mass of 1 mole of molecules. So this here, molar mass would then be equal to the formula mass, or formula units of that compound if you're dealing with ionic compounds. Right? Because ionic compounds do not contain individual molecules. That's where they're just like a grid. So we convert between the mass of a compound and the moles of a compound, and then we calculate the number of molecules or formula units from moles. We'll see more of what exactly that means. So the molar mass of a compound in grams per mole, I'll highlight these things, right? So molar mass of a compound in grams per mole is equal to the formula mass of the compound in atomic mass units. They're slightly different because of the definitions. Functionally, they're the same. So the formula mass of a compound is the sum of the atomic masses of all the atoms in the chemical formula. So the formula mass, sum of the atomic masses of all compounds, or all the atoms. So for calcium nitrate, our formula mass is going to be the mass of calcium. I'll do it like this. The mass of calcium plus the atomic mass of, I choose this example for this one because so we talked about counting the number of atoms in a formula, right? So if we have this 2 out here, we multiply everything in the parentheses by 2. So we have 1 calcium, so outside of that. We have 2 nitrogens. So we have our 1 calcium plus the mass of the 2 nitrogens plus the mass of 6 oxygens will be the formula mass for calcium nitrate. So calcium, where calcium is, 40.078. So this is calcium, right? 40.078. This is again grams per mole plus 2 times nitrogen, which I'm just going to use the one that I have memorized, 14.01 grams per mole plus, oxygen. So 6 times, we're just going to use 16.00 grams per mole. And that will give us the formula mass. So 40.078 plus 2 times 14.01 plus 16 times, sorry, not 16, 6 times 16. So this is 164.10 grams per mole. And then the molar mass, well, what's the molar mass then? I guess this is the molar mass. So it's also, I should have used atomic mass units, because technically these on the periodic table are AMU, but 1 AMU is 1 gram per mole. So the molar mass of calcium nitrate is 164.10 grams per mole. And then just to be clear, when I write grams/mole like that, that's the same thing as 164.10 grams per 1 mole. It just takes up way less space.
So was the answer for the first one, right?
It's the answer for both.
Okay.
Yeah.
So it's always the same for the formula
Yeah, they're always the same.
You said 1 AMU equals what?
Oh, 1 AMU is 1 gram per mole. Numerically speaking. Very technical difference there. But they're the same. And then, actually, to go back to this very briefly, so calcium nitrate will always have, this formula unit will always have the same mass of 164.10 because the masses of the atoms don't change. But it's not super useful to memorize the masses of those entire things because there's so many of them. You just end up calculating it every time. So we want to find the number of moles in a 22.5 gram sample of dry ice, which is solid CO2. So now we're combining all of these things. Our molar mass based on the formula mass, because here we're given 22.5 grams of CO2. And we want to find moles of CO2. So how do we get from grams to moles? It's the molar mass, which is formula mass. What are the units of molar mass? If it converts between grams and moles, the units have to be grams per mole. So molar mass is always in grams per mole. And then we'll calculate this for CO2 based on the atomic masses on the periodic table. So we can calculate that. So we have carbon, oxygen. So carbon, this is where, again, I'm counting the number of each type of atom. So if we have 1 carbon, 2 oxygens, carbon, we could look on here, but I know it. Carbon is 12.01. It says 1.01 or 12.011 there, but I'm going to use 12.01. And then oxygen is 16.00. So this is 12.01. And then we're going to add that to 16 times 2, 32.00. So we'll get 44.01 grams per mole. So we can create a conversion factor for anything or any compound as long as we know the number of each type of atom, which you should have in the formula, chemical formula. So now we can start with our 22.5 grams of CO2. Oh, just realized what time it is. Okay, 22.5 grams of CO2. And we're going to use now this conversion factor that we just created, we just calculated. And we want to get moles, and we have grams. So we're going to divide by 44.01 grams CO2 and 1 mole, or per 1 mole of CO2. 22.5 divided by 44.01. We get 0.511247, or we have 3 sig figs because 22.5 has 3 sig figs. It's going to be 0.511 moles of CO2. Cool? Good? All right. Any questions? Yeah.
So the process where we're using the number of atoms that is called like formula mass? We're using the formula mass,
That's calculating the
calculating,
molar mass,
which is also equal to the formula.
which is also equal to the formula mass.
Okay.
So from here on out, I'm going to use molar mass. Yeah, because it's molar mass, it's moles and mass, moles and grams, grams per mole. Yeah. Any other questions? No? All right. So, calculate the number of moles of nitrogen dioxide in 1.18 grams of nitrogen dioxide. So given 1.18 grams NO2, find moles NO2. Also, I don't think I said this explicitly, but the abbreviation for moles, it's not super short. It's just MOL. Doesn't do a lot, but it does a little. All right, so what do we do now? Yeah. Find the molar mass. Yeah. So nitrogen, we have one of those. For oxygen, we have two. So this one's 14. 14 actually, is it 14.01? I've always used 14.0. Yeah, it is. Okay. Times 16.00. So 14.01, 32.00. Then we add them together. Okay. Now it's our conversion factor. Yeah. Yep. I like this. You guys know what's going on. You're done? You're good? Let's do a final right now? I'll just start writing down problems. All right, so that, but 3 sig figs, 0.0256 moles. I don't end up doing a lot of scientific notation on here, right? So we have to move that decimal over. And usually we move the decimals so we have a number in the ones place and then the rest are decimals. So 2.56. Whoops. Yeah, -2. Good.
We use scientific notation because we're trying to get the same amount of sig figs, right?
Actually, for this, this is still the correct number of sig figs.
Yeah.
It's just, I haven't been doing it a lot, so this is an example.
Both of them would be correct, though, right?
Both are correct. It's only with large numbers that you have to use scientific notation, because there's no way to indicate which zeros are significant or not. Okay. How many molecules? Now, here we're mixing it up a little bit. Most of this is all going to be the same, right? We've got 3.64. Do this given real quick, 3.64 grams of H2O. And then right? Got our hydrogens, got 2 of those, got our oxygen, got 1 of those. We want to find the number of H2O molecules. So like with atoms, when you're asked for the number of molecules, that's going to involve Avogadro's number. But here we got 1.01, 16.00. This is going to be 2.02, 16.00. So we'll get 18.02 grams per mole of water. Everything's the same so far. Even up to this point, where we have 3.64 grams H2O. And then I'm going to divide by 18.02 grams, 1 mole. And then that would give us moles. But we want the number of molecules, which is going to be very similar to, well, calculation-wise, it's exactly the same as calculating atoms. Yeah, so this is going to be 6.022 times 10 to the 23. This is 1 mole.
And how did you get the 6.0?
That's our conversion factor. That's how much 1 mole is. So because we calculate this part would get us to 1 mole, then we want to go from moles to molecules.
And for 1 mole, that's it.
So this is why I said that 1 mole of something is 6.022 times 10 to the 23 of something. It could be atoms, and it could be molecules, it could be anything. So in this case, we want to go all the way to, and I'm not going to have enough space for that. We want to go all the way to molecules. 3.64, 6.022 divided by 18.02. 1 point, that was a sound. Hope it was a phone. Times 10 to the 23. Molecules is a long word. Okay, H2O. How many sig figs do we have? 3. Tres leches. Okay, 1.22 times 10 to the 23 molecules. So if you're asked for molecules or atoms, you're going to be using Avogadro's number. Now, let me ask you a question. What? Oh, did you have a question? If you're going to or from molecules or atoms, you're going to need Avogadro's number. And you're going to go through moles. Yeah, this is 6.022 times 10 to the 23 is Avogadro's number, is the number of moles, or number of things in a mole. Okay, so what if we take this a step further? How many hydrogen atoms are there? How many in this many molecules? Huh? Did you say 2 what? There's 2 hydrogens in every water molecule. How many hydrogens are there in this many molecules?
There's 2, so you would divide it by 2, right?
Close. Multiply by 2. Because for every single molecule, there's 2.
Oh, okay. That means for each single molecule.
Yeah, for a single molecule.
So you'd multiply by 2.
Yes. So this would be 2.44 times 10 to the 23 hydrogen atoms. And then if I ask you how many oxygens are there, it's the same.
Okay.
Right, because there's one oxygen per every molecule.
So you just multiply the 1.2 times the.
Times the number of hydrogens in this case per molecule. Yeah. So if there were 3, multiply by 3. Okay. What?
Oh no, it was upset.
Oh.
I'm totally sorry. Sorry, he's just seeing me working the fun out. Like, don't do that, please.
We'll see after Wednesday.
We'll see you again.
So you can do this. This is what I was getting at with the 2 atoms, right? There's 2 hydrogen atoms in every water molecule. It's like there's 3 leaves on every clover.
So you would multiply it by the 14 by 3 because
Yes. Getting ahead of me, but thank you. So for 14 clovers, if you want to set this up as the way we've been doing conversion factors, then there's, for every 1 clover, there are 3 leaves. So whatever 3 times 14 is. 42. So the only time that can get a little bit tricky is when you've got like things in parentheses. You've got to remember to multiply. So like if we had, we'll use the one from before, calcium nitrate. All right, so there would be 6 oxygens for every calcium nitrate. Yeah. So 8 legs per 1 spider, 4 legs per 1 chair, 2 hydrogen atoms per 1 water molecule. And we've talked about this also that, atoms and molecules are bound in certain fixed ratios, otherwise it would be a different molecule. So in something like carbon tetrachloride, wow. In carbon tetrachloride, there are 4 chlorine molecules, or chlorine atoms, for every chlorine tetrachloride molecule. All right, so these are inherent relationships. And just remember, we are going to go over like 30 minutes today. Then we'll head up to the lab. Don't feel bad if you do need to leave because your ride's here or something. This will be posted. So the formula for carbon dioxide, CO2, means there are 2 oxygen atoms per carbon dioxide molecule. All right, 2 atoms, 1 molecule. Similarly, there would be 2 dozen oxygen atoms per 1 dozen carbon molecules. Or there's 2 moles of oxygen for every 1 mole of carbon dioxide. So because each of those molecules has 2 of them, you can multiply the whole thing by 2. Or whatever the subscript is. Do that for a second longer. Good, 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 good. So we have 18 moles of CO2. How many moles of oxygen?
So there's 2 oxygens, correct?
Mm-hmm.
Carbon, and then you multiply by their masses, right? Or no?
Don't have to multiply by masses here.
Okay.
So when you're in moles, then you're counting in bulk individual atoms. So if we have 18 moles of CO2,
Oh, yeah.
it would be just 2 times 18, right? Because for every 1 CO2, we could even say 1 mole of CO2, we have 2 moles of oxygen. And so we can still make these units work out. So we've got 36 moles of oxygen. Good, good, good. So, for whatever reason, this gets a little, sometimes trips people up. It doesn't have to be whole numbers, because we can just multiply by 2, right? Or in the last case, we could multiply by 2. So if we have 1.4 moles of H2SO4, which is sulfuric acid, and we want to know the number of moles of oxygen, how would we do that? It's the same process as the ones we talked about before. So you have 4 oxygens, right, per sulfuric acid. So for 1 H2SO4, should write moles here, 1 mole. We have how many moles? 4 moles of oxygen. So we can just take our 1.4, multiply it by 4. I think it's 5.6. So 1.4 times 4, 5.6 moles of oxygen. I'll bring my water in. So that's an important point, because sometimes we want to know how much of just one element is in a compound. So say we have 2.4 grams, or sorry, this is worded a little bit maybe confusingly. What mass of sodium chloride contains 2.4 grams of sodium? So we'll start by writing down what we're given. We have 2.4, freaking out on me. 2.4 grams of sodium, Na. And we want to find a mass of NaCl. So mass sodium chloride. And I think this is one of the places too where if you follow the units, if you know what you're starting with, you know what you're trying to get to, you don't necessarily have to understand how to get there. Just try and work with the units you have, conversion factors that you have to get to that final answer step by step. So starting with this 2.4 grams of sodium, there's really only one thing that we can do with that, right? We can convert it into moles. So sodium has a mass of 22.99. So 22.99 grams per mole sodium. So we start with 2.4 grams Na. We can convert that into moles, divide by 2.99 grams Na per 1 mole. So that will get us to moles of sodium. Then how many moles of sodium are there per moles of sodium chloride? 1. It's 1 to 1. So we say for every 1 mole of sodium, we're going to have, or need, in this case, I suppose, 1 mole of NaCl. And then we want to get to a mass of sodium chloride. So we can say, okay, we've got a mass. We want to get to mass. We have moles now. So we can use the formula mass, or the molar mass. I said I would say molar mass. Use the molar mass of sodium chloride. So molar mass of sodium chloride will be, right, NaCl, 1 of each. This one's 22.99. This one's 35.45. Doing a lot of extra writing. Okay. So 22.99 plus 35.45 is 58.44, and that is grams per mole. That was a lot. Give you a second. Now we have, again, looking at where we've gotten at our equation, moles of sodium chloride. We can now use the molar mass of sodium chloride to convert to grams of sodium chloride. So we're going to do 58.44 grams of NaCl per 1 mole NaCl. So we're going to get 6.1007 grams NaCl, or using the correct sig figs, 6.1 grams NaCl. So that mass of sodium chloride has 2.4 grams of sodium in it. And really, just by manipulating the units, we can get from one thing to the other, which is asked for, pretty easily. So this is going to be a very, very common thing, that you're going to be given a mass of something. You'll convert it into, we'll say, let's call this mass of A. You'll convert it into moles of A. From there, you can convert to moles of something else, B, and then to a mass of B. Any questions there? Do another one then. So to determine the mass of oxygen in a 5.8 gram sample of sodium hydrogen carbonate. Fortunately, given the formula there. So if we're given 5.8 grams of sodium hydrogen carbonate, NaHCO3, and we want to find the mass of oxygen. So what should we do first? Anybody from the back? What have we done on all of these so far? Calculate a molar mass? Calculate a molar mass. So just the way I would go about thinking of this is, we've got a mass of this, and we want to get to a mass of something else. And again, in this situation, there's really only one way we can go, right? We can go from grams of this to moles of that. So to calculate the mass of sodium, hydrogen, carbon, oxygen, we have one of each of these and 3 oxygens. Sodium is 22.99, hydrogen is 1.01, carbon's 12.01, and oxygen is 16.00. All right, so we're multiplying the number of the element times the atomic mass of the element. 22.99, 1.01, 12.01. So 42, 48, 48.00. And then we add these all together. 1 plus. To get 84.01 gram per mole NaHCO3. Okay. So if we start with, I'm actually just going to start with where I have it written here. If we want to convert this convert our grams of sodium hydrogen carbonate into moles, do we divide or multiply by the molar mass? Divide. Grams NaHCO3. All right, so it's grams per mole, so we're going to get moles now. Okay, so if that gives us 1 mole, if that gives us the number of moles, sodium hydrogen carbonate, how do we find the number of moles of oxygen?
The number of oxygens, right?
Close, yeah. So let me write it out like this. So if we have, for every 1 mole of NaHCO3, you're definitely on the right track, right? We have 3 moles of oxygen. So if we have moles of sodium hydrogen carbonate, we want to divide by moles of sodium hydrogen carbonate and multiply by moles of oxygen. Okay. So now we've got that. How do we find the mass of oxygen? Yeah, the atomic mass. So for oxygen, it's 16 grams per mole. Right, 16, well, 0.00 grams oxygen equals 1 mole. So if we have moles here, we want to divide by those moles. 1 mole of oxygen, 16.00 grams of oxygen. So that should give us what we're looking for. Yeah.
You wouldn't use the 48, like that mass, because we multiply by 3? Like, I don't know.
I know what you're saying. Yeah. So that's the mass of 3 oxygens.
Oh, just 1.
So, right. So we just have, we can use just 1. You could use 48. I'm going to erase this again in a second. But, right, so 48 per 3, if you did 48 divided by 3, you'd get 16 divided by 1. 16 over 1. So it is the same thing. But we've already taken into account those 3 oxygens in this step. So we can use the simpler 16.00 and 1 mole. We do 5.8 times 3 times 16 divided by 84.01. It's that many grams of oxygen. And we have just 2 sig figs this time. So 3.3 grams of oxygen. And if we take a look at the structure of this again, we went from a mass of something to moles of something to moles of something else, more specifically moles of something in our first something, and then a mass of that thing. So that pattern of going from mass to moles to moles to mass is going to be very common. Any other questions? All right. I'm just going to introduce this concept. We'll do this first slide, and then we'll just repeat it next time we come back. So the mass percent composition, or mass percent of an element, is the element's percentage.
May I have your attention, please? This is Atlas IED.
So the mass percent of element X, or of that element, is the percent mass of that element in the total compound. All right, so we got mass percent of X is equal to the mass of X in a sample of the compound divided by the mass of the sample of the compound. So I'm going to flip back to this previous slide. So if we look at this, we've got sodium hydrogen carbonate, this mass, and then we've calculated the mass of the oxygen in that total compound. So if we take this 3.3, well, actually, this is one of those situations where if these were like a stepwise problem, 3.3 would be your reported answer. So that would be like the answer for A. And then if B was what's the mass percent of oxygen in sodium hydrogen carbonate, you should go back and use the whole number. Because you're doing another calculation, you don't want rounding error on top of that. So we should use 3.1389 grams of oxygen. So if you look at this, that's our mass of X in a sample of the compound. Then we divide by the mass of the whole compound, 5.8 grams of NaHCO3. And so we'll get 0.57 or 57%. So oxygen actually in this case makes up more than 50% of the mass of the whole thing. It kind of makes sense because it's not the lowest mass in there, it's actually one of the highest. And there are 3 times as many oxygen atoms as anything else. But you can't just determine the mass percent by looking at it, you have to calculate it, or it has to be given. So that's the idea of this mass percent. So we could take then any amount of sodium hydrogen carbonate, and if I said how much oxygen.
May I have your attention, please? This is Atlas IED.
Add a page. So if I asked you then how much oxygen is in, make it easy, 100 grams of NaHCO3, and I had just had you calculate, actually that's on the screen, and I had just had you calculate the mass percent, you can take a shortcut here. If we know the mass percent of oxygen is 57%, again, you should use the whole number, but we could do 100 grams of NaHCO3, and we know that 57% of that is going to be oxygen. So we multiply by the proportion. There's going to be 0.57, and that'll give us 57 grams of oxygen. So in a lot of cases, mass percent is very useful. Can't always use it, but when you're working with a lot of the same compound, for example, iron ore, a lot of ores will be done in percent of that ore. So that if you get a 100 kilogram block, you know it's 20% iron, then 100 kilogram? 20 kilograms would be iron in that 100 kilogram. And sort of tied to that is this idea of mass percent composition, or just mass percent. So that'll be how much of a single element contributes to the mass of the entire compound. So if we have a mass percent of element X, that's the mass percent of X in a sample of the compound divided by the mass of the entire sample of the compound. And then we multiply by 100 to make it a percent. One of the ways that you can do this, actually experimentally to determine it, is by taking a sample. So in this example, we have a sample of this much chromium, so 0.358 grams of chromium. All right, so chromium, its symbol is Cr. We react that with oxygen to form 0.523 grams of the metal oxide. So the metal oxide in this case being chromium reacting with some amount of oxygen. We actually don't know how many, so I'm going to put an X there. That's not OX for oxygen, that's O with an X number of those oxygen atoms. So if we wanted to calculate the percent mass of chromium in this sample, we'd say 0.358 grams of chromium. And that's the mass of X. So the mass of X there being chromium now, so the mass of chromium in a sample of the compound. And then we divide by the mass of the sample of the compound. So we divide by this other mass that we have, and that's 0.523 grams of our chromium oxide. So we can say CrOX. Or if you want to just write out chromium oxide there, you could do that also. So, oh good. I do have my calculator here. So we take 0.358 divided by 0.523, get 68, oh sorry, and then multiply by 100. So we want it to be a percent. We'll get 68, 3 sig figs here, 68.5% chromium. So that is the percent mass of chromium in chromium oxide. Any questions there? In the chat. Again, just feel free, oh, I guess if I put that there, that'll cover the screen. Feel free to, again, interrupt. If I ask if anybody's got a question, feel free to interrupt with a verbal question if you're brave enough. All right, so mass percent. The percent of the sample divided by this, mass of the sample divided by the mass of the whole compound. So we can use mass percent composition as a conversion factor between grams of a constituent element and grams of the compound. So the mass percent composition of sodium and sodium chloride is 39%. So we can write this as well, we could write it as 39% sodium. Or if we wanted to convert this into a conversion factor, you really multiply this by 100. Or sorry, not multiply by 100. So you do 30, we have 39, you'd have 39 grams of sodium in 100 grams of sodium chloride. And you could simplify that if you wanted. Or it would be the same thing to write, and I guess this would be simplifying it, but 0.39 grams of sodium in 1 gram of sodium chloride. So for any amount now of sodium chloride, if we have that mass in grams, we can convert that from grams of sodium chloride to grams of sodium. It's just a proportion of the whole. Any questions? So we go back to an example that we actually used, might have been in the beginning of this chapter. I always get mixed up on which chapter it is. All right, we asked this question, how much sodium chloride could you eat and still maintain or still be under the recommended amount of sodium per day? So the FDA recommends that you consume less than 2.4 grams of sodium per day. How many grams of sodium chloride can you consume and still be within the FDA guidelines? Sodium chloride is 39% sodium by mass. So we're going to be starting with 2.4 grams of sodium. And we do want to get to here, so because it's asking how much sodium chloride can we consume. So our given there, we want to find question mark grams of sodium chloride. And then we're also given that we have this 39% sodium by mass. So we can rewrite that 39% sodium by mass as a conversion factor and do that as 39 grams of sodium per 100 grams sodium chloride. And if you were thinking it, you can solve this using the molar masses, which is an example that we did earlier, but here we're specifically trying to use percent mass. So we start with our given number here, 2.4 grams of sodium. Now we have this conversion factor. So 100 grams of sodium chloride is 39 grams, is going to have inside of it 39 grams of sodium. So we can look at our units here. We said we have grams of sodium, and this is grams of sodium. And we want to get to grams of sodium chloride, and we have units of grams of sodium chloride here. So we can multiply this. You go ahead and answer in the chat real quick. Are we going to put grams of sodium chloride on the bottom or the top? So grams of sodium chloride, is that going to be on top or on bottom? Top, got 1 for top, 2 for top, 3 for top. All right. Yeah, we're going to put 100 grams sodium chloride on top, 39 grams of sodium on the bottom. Because now these units will cancel and give us the units that we're looking for. Now, one thing that I did notice on the exam, a lot of people missed, was setting up these conversions correctly, and specifically knowing which number went with which unit. So right on an example here, there was a problem where you had to convert from, what was it, kilometers, I think, to meters. And so I saw a lot of people write the conversion factor for this as 1,000 kilometers equals 1 meter. And I do understand how you got that, because kilo means 1,000. So a kilometer must be 1,000 meters. But, and that is the case, except it's not the kilo that's 1,000. This represents 1,000 meters. So the correct conversion factor should have been this. Now that one was maybe a little on the tricky side because you needed to know how to use the metric conversions. Okay, so going back to our problem here though, we have 2.4 grams, and we're going to multiply it by 100 and then divide by 39. So 2.4 times 100 divided by 39. And that's going to give us 6. Write that with a more permanent one. We have 2 sig figs here, so it's going to be 6.2 grams sodium chloride. Cool. I think the key on these is definitely converting from this 39% over to something like 39 grams in 100 grams. Makes the units a little more tangible than percents. No? Okay. Keep going. So we just did this math. Well, this math, right? So 6.2 grams of sodium chloride is really the max, according to the FDA, of salt, sodium chloride, that you should have and stay under their recommended limit of sodium. On this next problem, we have a woman who consumed 22 grams of sodium chloride. How much sodium does she consume? So we're going to have a very similar problem here. We've got our given, which is going to be 22 grams. Sodium chloride this time. Then I'll keep, as I remember things that I saw on the exam while I was grading it, I'll point these out. Make sure you know and study through your units and what the units are. I know in one of the questions, people were writing down gallons as G, but G is grams. So gallons should be GAL. All right, so we got this woman consumed 22 grams of sodium chloride. How much sodium does she consume? And then we want to find, right, how many grams of sodium. So then we can change our 39% again here into an easier to work with conversion factor. And it's going to be 39 grams sodium per 100 grams of sodium chloride. And for any of these conversion factors, you can do this. I'm sure we'll come across a few more, but when you have something like percent mass, percent is actually kind of a compound word in terms of its roots. You can think of it as two words, per and cent. So it means per 100. Cent equals 100. Whoops, that's 1100. So this is 39% sodium by mass. So we can convert that into 39 grams per cent or per 100 grams of sodium chloride. So similar problem to the last one, but now we're starting with grams of sodium chloride. And we're going to put grams of sodium chloride on the bottom or the top here. Bottom, yeah. The 100 grams sodium chloride will go on the bottom because we're canceling these units, right? It's not specifically that one over there, but this one, and we want to get grams of sodium as our answer. So we'll put 39 grams of sodium on top. So now we get 22 times 39 divided by 100. And we'll get 2 sig figs here, 8.6 grams of sodium. So she's had almost 4 times, if not exactly, not quite 4 times the daily recommended amount of sodium. It's going to have some high blood pressure. Are there any questions about using percents? Can also, if you want to use the hand raise, if you want to use ask a question and you don't want to interrupt.
Professor Kawagoa, I have a question.
Yeah.
So I have a question regarding the 39 grams of sodium divided by the 100 grams of sodium chloride. So when we do that, I'm putting in my calculator and I get 0.39. So I was just wondering, like, if we're like looking at it, would you cancel out like the grams on the top and grams on the bottom and the Na and the Na on the bottom to get the 39 grams of Na?
Yeah, and actually that's right. So percents, that's how percents work actually. They don't have units. You have to figure out what the units are based on the context. So in this case, the context is that it's 39, and that's why it has to say by mass.
Okay. So then that's how we're getting the 39 grams of Na.
Right.
Yeah, got it.
Yeah, so it's just this 39, and then it says by mass, so we know it's going to be grams of sodium. If the question did ask you, though, you could use, for a brief second, you could actually use any units of mass. So if the question was 22 kilograms of sodium chloride, we could use 39 kilograms of sodium per 100 kilograms of sodium chloride. So it kind of ends up being the same problem, if that makes sense.
Yeah, it makes sense.
Yeah. Good question, though. Any other questions? All right, let's keep on keeping on. I think my tendency is definitely going to be to go slower. Since last summer was the last time I did this fully online, I had hours to do the lectures. Okay, so we can also calculate mass percent composition from the chemical formula. So if we find the mass of 1 mole of a compound and the mass of the element in 1 mole of the compound, we can do really what's the same calculation as before, where we have mass of element X in 1 mole of a compound, and then mass of 1 mole of the compound. So we'll have to use the idea, was the last slide? Yeah, last slide or two of chapter 5, where it was the formula mass. All right, so for a compound, we can add up the masses of all of the molecules that comprise that compound, and use that as the molar mass. So we have acetic acid here, which is the active ingredient in vinegar. And we're asked to calculate the mass percent composition of O, or oxygen, in acetic acid. So this is a good quick refresher on how to calculate formula mass. I'm just going to write up the full formula here. HC2, H3, O2. And when you're doing formula mass, at least the way that I like to do it, is I'll write out the number of each type of element that I have first. So we have carbon, hydrogen, oxygen, doesn't matter which order you do these in. And then we have 2 carbons, we have 4 hydrogens, because even though this hydrogen is out front, it's really there to indicate that this is a acid, but it's still a hydrogen just like these ones. So we have 4 total hydrogens, oops, and then we have 2 oxygens. And then we can multiply these by their atomic masses. So for hydrogen, at least on this periodic table, we have it as 1.008. I'm writing that in on the slide, but I'll switch back to that in a second. For carbon, our mass is 12.011. And then for oxygen, it's going to be 15.999. So I'll switch back to the slides here. All right, so we've got, like I was saying, for carbon, 12.011. For hydrogen, 1.008, and then 15.999 is the mass for oxygen. Does anybody remember what these units are? If you want to type it in the chat or say it out loud.
Is it grams?
Close. It's grams per mole. So type that in the chat there. You use grams/mole. So grams per mole. I know it was last week. It was before the exam, and I know that after an exam, that's when the memory wipe takes place. Throw everything out, make some room for new stuff. But we have now 12. So just to write this out up here as well, right? 12.011 grams per 1 mole, and I guess these are each carbon. So that means that if you have 1 mole of carbon atoms, they're going to weigh 12.011 grams. And again, 1 mole is equal to the big number, also called Avogadro's number, 6.022 times 10 to the 23. So now that we have this down on the left, we can take these and we can multiply, right, the mass, or the molar mass, as by the number of that atom. So 2 times 12.011, and then, I'll write these out, 24.022, then 4 times 1.008, so it's 4.032, 2 times 15.999, 31.998. So in terms of sig figs here, the number of atoms in a molecule is an exact number. So our smallest number of sig figs when you're calculating a formula mass is going to come from the molar mass of that element. So for this one, we have 5 sig figs. For hydrogen, we have 4 sig figs. For oxygen, we have 5 sig figs. And that will depend on, in terms of exams, how many sig figs are on the periodic table that I give you. So the one that you had on the last exam is the one that you'll get on future exams. Actually, I have them right here. Oh yeah, so this is the same level of precision as that periodic table. Okay, so once we've multiplied these out, right, we get the total mass for each element individually. We can add those all together. So 24.022 plus 4.032 plus 31.998. So our total mass for acetic acid is 60.052, and that's grams per mole. And we keep all of those as sig figs because remember, when we add and subtract, we keep the smallest number of decimal places. And these actually all have the same number of decimal places. So that's grams per mole acetic acid. All right. So now to calculate the mass percent composition of oxygen in acetic acid, we'll go back to this previous slide. We want the mass of element X in 1 mole of the compound, and divide that by the mass of 1 mole of compound. So the convenient thing about using molecular weights, using molar masses here, is that this is 60.052 grams per 1 mole. So we have here now 1 mole, or the mass of 1 mole of this compound. So we can say, so this is the bottom, right? So this is 60.052 grams of acetic acid. So that's the mass of our whole compound, of 1 mole of our whole compound. And then we're looking for the mass percent composition of oxygen. So we actually have calculated that already. What is the mass percent composition? Sorry. The process called the abundance. No, this is the, so abundance, calculating atomic mass was the last question on the exam. If you want, I could do an example of that afterwards, or after we get through where we need to get to in this chapter, after we finish chapter 6. So this is calculating the formula mass. Yeah, I'll go over the exam stuff later. But it does look similar. So, okay, so we've calculated now, we need the mass of 1 mole of the element that we're interested in. So what is that mass going to be? And it is on the slide already. Yeah. Right. Thank you, Maya and Jocelyn. So yeah, it's this 31.998 grams per mole. So we have 2 atoms of oxygen in every molecule of acetic acid. So that's just going to be 2 times the atomic mass to give us this 31.998. So we do 31.998. And now we want for 1 mole, right? Because if we go back to this slide, it's mass of element X in 1 mole of compound. So this is grams per 1 mole. So if we have 1 mole, we have 31.998 grams of oxygen. So then shift this over a little bit. Do that. We can multiply now by 100 also, because we want this to be a percent. So 31.998 divided by 60.052. And we're going to get, oh, I didn't multiply by 100. We're going to get 53 point. Actually, we keep a lot of sig figs here, right? Because each of these is 5. So we have 5 sig figs that we're keeping. So 53.284%. Went skiing this weekend and my lips got super chapped. All right. So the key for calculating this is remembering that you do everything in terms of 1 mole of the compound. All right, so this is 1 mole of the whole compound. 31.998 grams is the amount of oxygen, the mass of oxygen in 1 mole of the compound. So it takes into account the fact that there's 2 oxygens per every acetic acid molecule. I guess this should be 53.284% oxygen by mass. Okay, moving on. So, right, we just did this. We can calculate mass percent composition from the chemical formula. And we can also calculate a chemical formula from the mass percent composition. And we talked about this before. This is the empirical formula. So this is the simplest whole number ratio between the elements. It's not necessarily the actual number. That's the molecular formula. So we're going to do the empirical formula, the molecular formula, just to give you this contrasted definition. Molecular formula. Wow, spelled that really bad. Okay, the molecular formula is the exact wow. Is one side of my face drooping? Am I having a stroke? The molecular formula is the exact number of each type of atom in a molecule. Wow. Struggling with the spelling. All right, so that's the molecular formula. Whereas the empirical formula is the simplest whole number ratio. An empirical, there's a definition of empirical here, right? It's derived from or guided by experience or experiment. So when you do an experiment, and we will have one of these, it's easier to come up with the empirical formula than it is to come up with the molecular formula. All right, I think I fumbled through the spelling of all those words enough that I think you had enough time. So an empirical formula only gives the smallest whole number, oh, it's on the next slide, of course, of each type of atom, not the specific number of each type of atom. Whereas the molecular formula always gives you a whole number multiple. Well, okay, that's not exactly what I wrote. So molecular formula will be a whole number multiple of the empirical formula. So hydrogen peroxide is a good example. Hydrogen peroxide is H2O2. If you were to do the simple experiment to get the ratio of the atoms, you would get HO. All right, so this is equal to 2 times the empirical formula. Because we have 2 hydrogens, 2 oxygens. So if we have a sample of water that is decomposed in the laboratory, I think this is the one that I mentioned. Yeah, look, they got a battery. That's a 6-volt battery. You can do this with a 9-volt battery also. So we have a sample of water that's decomposed in a laboratory, produces 3 grams of hydrogen, 24 grams of oxygen. How do we determine an empirical formula from this data? Actually, is it on the next slide? No. So how might you do this? I have my chat window over here, that's why I'm looking over here. So we know that in a molecule, we're always going to have the same number ratio of atoms of each type. So for water, we know that there's hydrogen and there's oxygen. But the mass alone, without converting it to anything, doesn't really tell us anything about the ratio, because the masses of each element the molar mass of each element is different. So if we look at this periodic table again, we can see that hydrogen is 1.008 up at the top left, and then over on the right side, oxygen is 15.999. So we can't compare them directly just using masses. But we can put them into a scale where they are equivalent. We can convert these into the number of moles of each type of atom. So if we have 3 grams of hydrogen, 3 grams of hydrogen, we can convert that into sorry, to think about this. Let's see here. Okay, right. So if you remember hydrogen and oxygen, and I think this actually might work out the same way either way. Hydrogen and oxygen actually exist as they're the molecular elements. So if we have 3 grams of hydrogen, 24 grams of O2, so they each exist as H2 or O2. It's 2 atoms bound together. So when we use the molar mass, we have to use the molar mass of H2, which, just to be quick here, is going to be 2.02 grams, and that's 1 mole of H2. All right, since there's two hydrogen atoms, then 1 mole of hydrogen atoms is going to weigh, or the hydrogen molecule is going to weigh 2.02. So then we get 3 divided by 2.02, that's 1.48, I guess technically 1 sig fig there. Oh, 3.0, 3.0, good. So that's going to come out to, with sig figs, 1.5 moles of H2. And then for oxygen, it's going to be 32.00 grams of O2 and 1 mole of O2. Again, the mass of a single oxygen atom is 16.00 or 16.999. H2 and O2, I think this actually works out if you do it the other way also, but hydrogen, or if you remember Brinkelhoff, BRINCLHO and F. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine all exist as diatomic, or they exist as diatomic elements, or the molecular elements. So they all exist as Br2, I2, N2, Cl2, H2, O2, F2. So when it comes out of the water, yeah, it's going to form those. So then 24 divided by 32 is 0.75. So now we can take our ratio of hydrogen, and again, this is going way, way back, but I mentioned that when you are looking for a ratio between two things, you generally want to end up with a whole number. So you divide the larger number by the smaller number. In this case, we have 1.5, and we'll divide that by 0.75. And this is going to tell us the ratio between these two numbers, or between these two quantities. So it's 2. So we have, and this actually becomes 2 to 1. So it's 2 moles of H2 for every 1 mole of O2. Or in this case, we have 2 hydrogens for every 1 oxygen, which is what we know water to be as H2O. I guess here you could have done it as H. So you get 3.0 divided by 1.01. Then 24 divided by 16. Yeah, so it would have worked out even if I hadn't done them as the diatomics, at least in this case. So by determining the masses of these things, when we decompose it, we can figure out the ratio between those elements. In this case, 2 to 1. And that would be our empirical formula. Any other questions there?
Is that where you got the 2.02 grams? Is from the mass of the element? The
Yeah.
2.02? Okay.
Yeah, so 1 hydrogen is 1.01, or I know I used 1.008 earlier. So 2 hydrogens would be 2.02. All right. And again, I think I mentioned this earlier, but if you're, make sure that your name on Zoom is at the very least your first name or something that I can match to the roster, so that I can take attendance that way. Okay. Right, so when you want to obtain an experimental formula or an empirical formula from experimental data, start with the masses of each element present in the sample of the compound. So that's what we did, right? Previous slide. Then I converted each of those masses to moles using the molar mass as our conversion factor. So the one, special case is for hydrogen or Brinkelhoff, any of those, where you generally want to use the bimolecular or the diatomic. Then you divide all of the moles by the smallest number of moles. If the moles are not whole numbers, then you have to multiply all the moles to get whole numbers. So that's what this table is on the right here. If you get you'll get something with a 0.1, you actually need to multiply that by 10 so you get a whole number. So once you have whole numbers on everything, write the formula using the numbers of moles as subscripts. Right, so subscripts being like H2O, right? This is a subscript. And then also, key thing on step 4 here is that you multiply all the moles to get whole numbers. So that means that if we had, like the example we had earlier with hydrogen peroxide, we had H and O. If you had one, I guess that's not a great example. We'll get to an example. So you would have to multiply the number of moles of hydrogen by 2, as well as the number of moles of oxygen by 2. Oh, of course. I just did this, but now that we know, I think this will be good actually. Now that we've walked through these steps, let's go through this one again. All right, let's rehash this. So decomposition of water, 3 grams of hydrogen, 24 grams of oxygen. So we have our 3.0 grams of hydrogen, 24 grams of oxygen. And then, so we're going to convert these. All right, first step is start with the masses of each element present. Convert each mass to moles using the molar mass as a conversion factor. So for hydrogen, now I'm second guessing the fact that I used H2 and O2 before. I know for this example it works, but that's because they're both bimolecular or diatomic. We'll do more examples and we'll see what happens. So 2.02 grams of hydrogen, H2, 1 mole. I think it works out the same. And 1 mole of H2. I'm really second guessing this. Let's actually do this example. Let's do this example real quick. Because it's going to be essentially the same thing. So if we take 165, actually let me do this off screen first. That's going to be 165. Sorry, I just want to make sure that I'm not leading you guys astray. Because otherwise that's 1.01, and that's different. Would be 220.2. Yeah, that makes more sense. Okay. I'm gonna have to look up more justification for why here. Yeah, I'm gonna have to look some stuff up here. Yeah, the math here would work out the same if you use just H and just O, but that's because they're both, right? Because if we did both of them as H2 and O2, then it's just double what it would have been, and it'll reduce down to the same thing. On this next example, we have carbon, and carbon's not diatomic, so it doesn't form C2. So you get a different number if you use, right, just carbon and then 27.8 grams of H versus H2, or 220.2 grams O or O2. So if these are doubled, then the mass is different. Which is because it just has O here. Because this ends up being All right, just use H and H2. We will get, or just H and O. All right, so single hydrogen, single oxygen for these. So this is 1.01 grams of hydrogen. And then this is 16.00 grams of oxygen per 1 mole oxygen. Because otherwise the numbers don't really make sense on the next problem. So then we have 3 divided by 1.01. So it's going to be 2.97. Or I guess in this case, if we were to use the correct number of sig figs, this would be 3.0. So it doesn't change. Then 24 divided by 16 would be 1.5. So this is moles H, moles oxygen. So then the next step is going to be divide all the moles by the smallest number of moles. So we're going to get our 3.0 moles, and we're going to take 3.0 moles H, moles H divided by 1.5 moles, divided by 1.5 moles of oxygen, and then we're going to do 1.5 moles oxygen divided by 1.5 moles oxygen. So then your smallest one will always end up as 1. Yeah, 3.0 because of sig figs. So our smallest one's always going to end up as 1. So we're going to have 1 mole of oxygen, and we're going to have 3.0 divided by 1.5 is going to be 2 moles hydrogen. So then our ratio of elements is 2 hydrogen to 1 oxygen. And so we can use those numbers then as the subscripts, and we get H with a subscript of 2, and O with a subscript as 1, but leave the 1 off. Are there any questions? Be a little bit surprised at this point if there weren't.
I have a question.
Yeah.
So I know like the last problem, you did H2O and then O2, right?
Yeah.
Okay, so I don't know, that kind of got me confused. So that you used 2 because of like BR, something like that. It was like BR2 and then I don't know.
Yes.
But it was because of that. And so this is a totally different problem, and that's why we didn't include like a subscript. Maybe.
Yeah, so I didn't write these slides. My instinct would be to use the 2, but
Okay.
because when you do split the water apart, that is what happens chemically. The fact that this slide is written with hydrogen and oxygen, not as H2 and O2, makes me think that this slide in particular is saying, oh, just use 1.01 and 16.00, right? So use the H and O rather than H2O2.
Okay, got it. Thank you.
Mm-hmm. And yeah, we're gonna see. Well, I'll show you on the next slide how that can make a difference. So this problem, again, similar type of problem, and again, similar thing happening here where it's grams of oxygen, and it's an O, not an O2. But hydrogen is just of hydrogen. So I'm going to assume that on these, that this is hydrogen, just H, and oxygen, just O. So if we have a sample of this different compound now, it's carbon, hydrogen, oxygen. I've already written those masses out over here. And that's our first step. Let's write out all of the masses. And then we're gonna have 165 grams of carbon. And we're gonna convert each of these into moles. So for 165 grams of carbon, we're going to divide that by 12.01. Grams of carbon is 1 mole carbon. For hydrogen, we're going to do 1.01. Grams of hydrogen is 1 mole of hydrogen. And for oxygen, we're going to do 16.00 grams of oxygen is 1 mole of oxygen. So if we do it this way, 165 divided by 12.01, that's going to be 13.7. This is now moles of carbon. We're going to do hydrogen as 27.8 divided by 1.01. That's going to be 27.5.
I have a question.
Yeah.
So you put 13.7 because of the number of sig figs, correct? Because I know when you like calculate that, it's a long number.
Yes.
So you wouldn't just, well, I know sometimes you say just like leave it as like the big number because I guess you're gonna add them all up. But in this case, just use the number of sig figs, correct?
Yeah, in this case, you can use the number of sig figs because we're going to divide them and get a ratio anyway. And usually it actually comes out a little cleaner if you round them here.
Okay,
got it. It will not hurt if you don't round here and do the math anyway.
Oh, okay. Sounds good. Thank you.
Okay, so now we can take these and we're going to divide by the smallest number. Maybe this one does go the other way, but I'm pretty sure it goes this way. We're going to take these and divide by the smallest number of moles. And really 13.8 and 13.7, very, very marginal difference there. Oh, I wrote hydrogen here. It's oxygen. just go by the actual smallest one, right? So the 13.7. So we'll do 13.7 divided by 13.7 moles of carbon, and then we're going to do 27.5 moles of hydrogen divided by 13.7 moles of carbon, and we're going to do 13.8 moles of oxygen divided by 13.7 moles of carbon. So this first one is going to be 1. Our second one is going to be right around 2. It's going to be 27.5 divided by 13.7. And it comes out to 2.00729927. But if we wanted to, we keep 3 sig figs here. But we're going to, if you're within less than 0.1, then you're going to round it to a whole number anyway. Because we can only have whole number ratios of our atoms. And hopefully there will be an example here. I think there is. I think there should be. But I don't remember if there actually is. Where we actually have to round this. So this is our moles of hydrogen. And then 13.8 divided by 13.7 is 1.007. So again, we're going to round that to 1. So we're going to have these numbers of moles of carbon, hydrogen, and oxygen. So our empirical formula, we just use those numbers as the subscripts. So it's going to be carbon with a subscript of 1. So we leave that off. Hydrogen with a subscript of 2. And oxygen with a subscript of 1. I've just taken these numbers, the ratio that we calculated here, and used those as the subscripts. Last one is also 1. Yeah, so it is, I guess I kind of answered this already, but it is 2.01 with sig figs, but we round then to whole numbers. If you go back to this slide, right, so if it was 2.1, or maybe like 2.9, or even like, I guess, 2.05, then you maybe would round it, say it's like that 0.1. That kind of gets into iffy territory. I need to come up with a better rule of thumb for judging those really, really marginal differences. Most of the time, though, you'll get something like, using the 2.0 will be like 2.08. You would maybe round that up to 2.1, then multiply by 10 to get a whole number. Definitely, if you're that, I will say that's not going to happen very, very often. This is 0.1, but you might get 0.2, 0.33 comes up a lot. 0.66 might even come up. So if you're in those in between numbers, definitely make a note that you should come back and look at this table. Not sure if this one, I'm assuming it's in the book somewhere in chapter 6, but for these, we are just rounding them to the whole number because they are very, very, very close to just a whole number. I did say I would do this, so I'm going to duplicate this page, copy, paste. Okay, so if we did this a little differently, let's back up here. So we're going to erase this and this and this. We're actually going to erase this and this. We're going to redo these ones. And let's assume that we have now, we'll do this in red, that this is H2 and this is O2. So this is 2.02, and now this is 32.00. If we redo these numbers, we do get something different. So we do 27.8 divided by 2.02. Now this is 13.8, and 220.2 divided by 32 is 6.88. So now if you remember, our second step here should be to calculate or to divide by the smallest number of moles. So our smallest number of moles is no longer 13.7, it's 6.88. So we will divide these then by 6.88 moles of oxygen. Now this is 13.8 divided by 6.88 moles of oxygen. Sorry, these are O2, H2, and 6.88 moles O2, 6.88 moles O2. So now our ratios, so 13.7 divided by 6.88 is going to be about 2, and it's 1.99. So again, that's more than close enough to just call 2. 13.8 divided by 6.88 is going to be 2.005. So again, that's 2. And then our oxygen here is going to be 6.8 divided by 6.88. So we're going to get 1. So that changes the compound. So we get 2, 2, and 1. And to me, this, I mean, that could be the empirical formula for something. I think that it is more likely that what we had previously was the case. So this previous slide, I'm actually pretty sure that this is correct. Make a note to myself that I need to come back and change this slide. Because I think that you should be able to recognize that hydrogen is a diatomic, it's a molecular element, because we went over those. So for exams, I will give you whether or not this is going to be H2 or O2, that kind of thing. That is annoying. Okay. So, moving on though. Ibuprofen, an aspirin substitute, has the mass percent composition of 75.69% carbon, 8.80% hydrogen, and 0.15.51% oxygen. Calculate the empirical formula of ibuprofen. So let me take, keys are bothering me. Any ideas of where to start on this problem? So these are all percent mass. And we did see earlier an example, divide by 100, okay.
Do we have to turn the percents into like grams?
We can turn the percents into grams, yeah. So this is, maybe I'll do a better job of saying this. This is one of those problems that when I was taking general chemistry at COS actually was an aha moment for me. You can just take these and convert them very easily straight into grams. Because if you think about this percent composition, it's kind of like what we did before where we said, what exactly did we do? Figured out the number of, because we had that was the sodium, right? So we had 39% sodium. And we just assumed that we had 100 grams. And so we said 39 grams of sodium, in that case, 100 grams of sodium chloride. And you can do that here as well. So if we assume that we have 100 grams of ibuprofen in this case, that's our compound that we're working with, then we would have 75.69 grams of carbon. And we would have 8.80 grams of hydrogen. and we would have 15.51 grams of oxygen. Now, where this problem differs, in terms of going back to this confusion about, is it H or is it H2, is it O, is it O2? In those previous problems, we were dealing with things being decomposed. So there's a chemical process happening that's splitting those apart into the constituent components. In this case, we're just told that our compound, our formula, which is going to be C with X, H, X, O, X, we're told that these are the exact percent masses inside of here. So in this problem, we're just going to use, and I know this one for sure, just hydrogen, just oxygen, not H2, not O2. The steps are the same though. So after this, you really do just say that this 75.69%, change that into grams. If you want a better, let's see, if you want to see how that's done so that the units work out, all right, we're assuming 100 grams of ibuprofen. And we know that it's 75.69%. So it's 75.69 grams of carbon per 100 grams of ibuprofen. Sorry, if you're on a phone, that's probably super small. All right, so it's up here. I wish this wouldn't cut off the top. I do that. All right, so 75.69 grams of carbon per 100 grams of ibuprofen. So if we have, and that's again the percent, which is per 100, if we have 100 grams of ibuprofen, then this is 100 times 75 divided by 100. So if you have 100 divided by 100, those cancel out, and we're left with the 75 grams of ibuprofen. I think that's where it was before. Okay. Sorry, a lot of explanation there. So what's our next step here? Yes, and I'm sorry I did not upload the beginning of chapter 6, but now that I have the end of chapter 6, I'll upload them together. Oh, it's 6:16. Oh, we have 8 slides left. Okay. Let's get through this. So our next step here is then to multiply this, or to convert all of these into a number of moles. So our mass of carbon, 12.01 grams of carbon is 1 mole carbon. So this is 1.01 grams of hydrogen is 1 mole of hydrogen. And then 16.00 grams of oxygen is 1 mole of oxygen. So we get 75.69 divided by 12.01, and that's going to give us 6.30 moles of carbon. 0.80 divided by 1.01 is going to equal 8.71 moles of hydrogen. 15.51 divided by 16 is going to equal 0. Well, I guess correct sig figs on the first one, right? Should have been 4, but I only used 3. 0.96. This should be 4 sig figs also. 4 moles of oxygen. So our next step here is going to be dividing then by the smallest number of moles, dividing everything by the smallest number. So 6.30 moles carbon. So then divide by 0.9694 moles of oxygen. 8.71 moles of hydrogen divided by 0.9694 moles of oxygen. then 0.9694 moles of oxygen divided by 0.9694. Okay. We start with the first one, which is the easiest, or start with this one, which is the easiest. That's 1 mole of oxygen. 8.71 divided by 0.9694. I'm gonna write this one out because I think it's a 9. Sorry, not 8, 9. It's 8.98, and then 6.3 divided by 0.9694. This is going to be 6. Whatever, we'll do 6.499. Okay. So I wrote out this 8.98 because while it's farther away than some of the other ones that we saw, which were like 0.99, again, it's still, only 0.2 away from being 0.02 away from being 9. So we can easily round that one up to 9. I'm running out of space. Let me this, we move that over. This.
I have a question for the first one. I don't know if you said it, but it was supposed to be 6.302. That's like the correct number of sig figs, but right now it doesn't matter, right?
Yeah, that is the correct number of sig figs. Yeah, I did not do the correct number of sig figs. You said it was 6.302. I'll put it in there now. So, like I was saying, we can round this one up to 9. This one stays 1. Sorry, this is moles of hydrogen. And then this 6.499, again, we can round that to 6.5. This is moles of carbon. So around the 6.5 moles of carbon. So now we have to check to see if we have whole numbers. And we do not, right? We have 6.5. So if we want 6.5 to be a whole number, you could go back and refer to that chart, but we can multiply this by 2 and we'll get a whole number. So still don't have enough space. We don't just multiply that one by 2. We have to multiply all of these by 2. Try to give myself a little bit more room here. So we multiply every one of these by 2 because we need this one to be a whole number, but we need to maintain the same ratio between them. So this 6.5 multiplied by 2 is going to be 13 moles carbon. 9 moles of hydrogen times 2 is going to be 18 moles of hydrogen. And 1 mole of oxygen will be 2 moles oxygen, which I know is just tiny enough to the side. So our ratio, or our empirical formula then, we're going to have carbon, hydrogen, oxygen. And now, because we have whole numbers, we can use those as our subscripts. So 13 carbons, 18 hydrogens, and 2 oxygens is the empirical formula. Any questions on that one?
I'm sorry, I have a question.
Go for it.
So I know when I said like, oh yeah, you divide by 100, but in this case, that's not what you do, correct? Because you're just multiplying by their masses and then you're trying to convert into moles and grams. Yeah,
so we started out, so I know what you were thinking.
Okay.
Because if we're using percentages, you almost always want to use them as a decimal number, not as a percentage. So you would divide by 100. In this case, if you divide by 100, you do get 0.7569 as your number.
Uh-huh.
But again, if we assume that we have 100 grams of ibuprofen, and you can use any number there, really. 100 is the easiest because then we can just say it's 75 grams. If you multiply 100 by 0.7569, you get 75.69. Right? 'Cause we divided it by 100 and then multiplied by 100.
Okay, got it.
Yeah.
Thank-
So it's just the fact that we're assuming, and if you want to try this, if you want to try it out, do it with like 3 grams of ibuprofen and then calculate how much mass, carbon, hydrogen, oxygen you have in 3 grams of ibuprofen. And you should end up with the same answer here. Okay. Let's move on. Let me see what we have going ahead here. Really need to finish this. Oh, it's a lot of examples. Wait, what is this? This is lab report 3. Okay. So we have a 1.56 gram sample of copper, reacts with oxygen to form 1.95 grams of the metal oxide. What is the formula of the metal oxide? So this problem has some of the information that we need just a little bit hidden. It's like the previous problem where we have, where we got to a mass of each of the constituent elements. But we're hiding it a little bit with the process in this word problem. So we've got 1.56 grams of copper. That one's pretty easy. The other thing, though, we have here is oxygen. And we're not given the exact mass of that oxygen. It's not 1.95. We're also told a metal oxide, so that's going to be any metal with oxygen. In fact, the lab that you're going to do, I think not next week, but the week after, because next week's a holiday, you'll do something very similar to this. So how do we find the mass of the oxygen? If we're going from copper plus oxygen to some sort of copper oxide, unknown number of coppers, unknown number of oxygens. We don't know the ratio. So when we react this copper with the oxygen, we're adding oxygens, just like it's written out here, we're adding oxygens to the copper. So if the mass goes from 1.56 to 1.95, all of that mass that we've added is oxygen. So we take the mass of our metal oxide, 1.95 grams, minus the 1.56 grams of our copper sample, and we'll get 1.95 minus 1.56, 0.39 grams of oxygen. And this is similar to the previous problem also in that this is oxygen that's part of the copper oxide, so it's not elemental oxygen, so it won't be diatomic. Again, I'll give you whether or not it's diatomic because these slides have been confusing. So we have 0.39 grams of oxygen in addition to our 1.56 grams of copper. And then the next step is the same as all the other problems we've done, but I need to find the mass of copper, which is 63. I'm going to use 63.55 because I'm already running out of space on these slides. So 63.55 grams of copper is the mass of 1 mole of copper. And then for oxygen, there's going to be 16.00 grams of oxygen, 1 mole oxygen. So 1.56 divided by 63.55, and that's going to give us 0.02 0.0245 moles of copper. 0.39 divided by 16 is going to equal 0.024. Well, I guess that should be just 2 sig figs, right? Moles of oxygen. So now we need to divide by the smallest number of moles. And if you have a hard time with telling which one's smaller when it comes to decimal numbers, you can always subtract them on your calculator. If you get a positive number, so if we do 0.0245 minus 0.024, which this is going to be 0.0245 minus 0.024. This is a positive number, it's 0.0005. Then the first number is larger than the second number. If you get a negative number, then the first number is smaller than the second number. So in this case, we know that 0.0245 is larger than 0.024. So we're going to divide both of these by 0.024. Although you can probably already see where this is going. 0.0 moles of oxygen. Copper, or sorry, this is oxygen, divided by 0.024 moles oxygen. Okay, so when we divide those, this equals 1 mole of oxygen, and this is going to be right around 1 mole of copper. So our formula then, where we can replace these x's now with the number of moles, we're going to have copper, 1, oxygen. So very easy to write these copper oxide problems or metal oxide problems. You're always going to get 2 of the numbers, and then you need to find the third number by subtracting. Just need to remember that you have the metal, the oxygen, the masses of those 2 together equals the metal oxide mass. Conservation of mass. All right, the last concept here to cover is how we get to the molecular formula from the empirical formula. So we need the molar mass to find what this whole number multiplier is, right? So our molecular formula is always a whole number multiple of the empirical formula. So molar mass divided by the empirical formula, or the empirical formula molar mass gives us N. So the empirical formula is always going to be smaller than or equal to our molar mass. And just like when we get a fraction, we always have to multiply all of the numbers by that multiple to get our molecular formula. So let's say we have the empirical formula for fructose is carbon, hydrogen, oxygen. So remember, empirical formula is the smallest whole number ratios. And we get a molar, we know the molar mass is 180.2 grams per mole. What is the molecular formula? So we're going to do, we need the molar mass, which we've been given, divided by the empirical formula mass. So we can calculate that by, all right, carbon, hydrogen, oxygen. It's just like calculating the formula mass for any compound. So we have 1 carbon, 2 hydrogens, 1 oxygen. So 1 carbon times 12.01. That's the molar mass of carbon from the periodic table. And then hydrogen, 2 times 1.01. And oxygen, we have 1 oxygen there, times 16.00. and then we're going to add those together. 12.01 plus 1.01 plus, oh, sorry. Oh, I guess I do want to show you this. I'm sorry, I put this in the wrong spot. This goes over here. Just we're gonna get this, 16. So the total mass there is 30.03 grams per mole. So that's the molar mass of our empirical formula. So that's our empirical formula mass. The thing I wanted to show you is that when you type this into your calculator, you don't actually need parentheses. You could type 1 times 12.02 plus 2 times 1.01 plus 1 times 16.00 without parentheses, because it'll do all the multiplication first and then it'll add everything together. And it doesn't matter that these are ones, they could be anything. Okay, so now we have our empirical formula mass. And we take our molar mass of 180.2 divided by our 30.03. So our molar mass divided by our empirical formula mass, 180.2 divided by 30.03. And that's going to be just the whole number here written out as 6.000666, right? So that's going to be 6. This is always going to be rounded to a whole number. So if we round this to a whole number, we're going to get 6. Now we need to multiply all of the subscripts in our CH2O by 6. So C in our empirical formula has a subscript of 1. So 1 times 6 is 6. Hydrogen now gets 12 because it's 2 times 6. And then oxygen now has a subscript of 6. And that this now is our molecular formula for fructose. All right. Okay, so we actually have just one more slide, last slide here. Now we've gone over a little bit. Butane is a compound containing carbon and hydrogen, used as a fuel in butane lighters. Its empirical formula. Empirical formula, so simplest whole number ratio, is C2H5, and its molar mass is 58.12 grams per mole. Find its molecular formula. So again, we're going to write this out. I want to find the empirical formula mass, which we find the same way as a molar mass, or formula mass, I mean. So we have 2 carbons, we'll shorten H, that's 5 hydrogens. So this times 12.01 times 1.01. So these are 24.02 and 5.05. So this is 29.07 grams per mole. And then it's again going to be our, come on now, molar mass divided by empirical formula mass. So 58.12 divided by 29.07. So 58.12 divided by 29.07 is 1.99931. And again, when we're looking for this ratio, it's going to be a whole number. So this is going to be 2. Variations here is just experimental error or the result of rounding error in some cases. So 1.99931, we got 2 now as our ratio. So in our formula of C2H5, we multiply all of those coefficients, or all of these subscripts by 2 to get C4H10. Are there any questions about that? I would recommend going back and finding these slides blank, probably even not today, but do it tomorrow, and try to run through these problems without looking at how I've gone over them once the video is posted. And that's going to be the best practice for, do I actually know how to do this? Without any help, without any notes. Or just notes.